This time we'll start looking at the surface integrals, which are even more interesting than line integrals because there are 2 degrees of freedom, 2 dimensions. And in this case, to describe the surface we need 2 parameters, s and t, for our position vector. And like we did for line integrals, we divide our surface into small elements, and also each element has orientation, which we normally take an outward orientation. And then we write our integral, as you have seen in the previous videos. We write it as a scalar product of the vector field and an element of that surface. So the task before us is to define what that element is. So how to define that element? What we should note is that if I take a derivative with respect to s for the fixed t parameter with respect to t, then we'll get respectively the tangent directions. And these 2 vectors, they lie in a tangent plane to the surface. And if we take a vector product between these 2 vectors, the cross product, then the vector will be normal, orthogonal to the surface. So that's one thing to bear in mind. And if we now try to fix one of the parameters and vary the other one, let's say we fix t and vary s a little bit, when we move along a curve on that surface a little bit, and then we can define a small vector in which direction we moved, which will be the tangent times this little change. And likewise, if we fix the s parameter, we can move along the direction defined by varying in t, which is another vector, let's call it delta m. And if we take these things together, we will get a small parallelogram. And what we're interested in is we want to understand the area and the orientation of that parallelogram. Well, we know that if n was a vector perpendicular to the tangent directions, if we multiply each tangent direction by a little bit to get these 2 vectors, it still will be perpendicular to both of them, the n vector. And if we write them as a cross products, then that would actually give us the element of the surface. And it has the right magnitude and the correct direction. Now that is a little parallelogram with some angle between. So let's think of a sketch to get a better feeling of what this little element of the surface look like. So let's plot our surface and take a little element along it. So we have 2 directions which define the surface. So let's say this is the s direction and this is a t direction. Again, like a latitude and longitude as we travel on the surface. And we can take a small element like that, and then we'll get the 2 tangent directions. So that one is dr over ds, and that one is dr over dt. And we had a normal to the surface, which is we call n. And if we look at this parallelogram even closer, then its size here is the magnitude of the first direction times little change in the direction of the travel. And likewise, in that direction, we have dr over dt times small change in delta t. And we also have an angle theta here. So that is our little element, that is ds. And if we want to not just the area but orientation, then we say, okay, ds is a normal times a change in these parameters. And we can also write it as the cross product, the vector product. Times little change in the parameters, right? As we tend these directional changes to the zero, it becomes an element of the surface which we can use for integration. So that is really a key point here, that gives us the right element of the surface and its orientation. So that's all which you need to understand about how we get to the surface element. And if we put it together, we get the definition of the surface integral, not only the definition but also a recipe. So now what we do is we change the generic form to the double integral by replacing this element with the cross product, the vector product. So it's very similar to what we had in the line integrals, but instead of this just the derivative, we have the cross product of the derivatives because we have two parameters. This is the most generic form, and there are cases where it looks simpler. So let's look at a case where we have a simpler way to define surface integral. And that is the case where they integrate parallel to a particular axis. So let's say we fix the z coordinate, so we have a fixed z plane. And in this case, every surface element will have orientation looking upwards in the z direction. So we have that expression for the element of the surface, or if we take the limit, and that brings us to just the standard double integral with respect to x and y. So that will just reduce to the standard double integral, and there is no surface integral left. So this is the simplest possible case. Let's look at the example. So let's look how to calculate surface integrals in practice. We're given the vector field, we're given a parametric form for the surface and the range of the parameters, and we're asked to compute a surface integral. Well, let's use the definition. So we first need to find what is the derivative with respect to s. So we differentiate first with respect to s, then with respect to t, and then we put it together using the cross product, and then the cross product of that will be k towards z direction, and that gives us the right expression for the surface element. So it's again will be only one component, so pointing upwards. And then we use the definition, so that's by definition. So we had this little element of the plane, so this was I, this was j, and we got k. And we use by definition, so that was our little element. With the orientation. So all that remains for us to do is to substitute something inside the vector field. So let's do that. So we have an integral which we found to be from 0 to 1, f with respect to the vector field inside it. It will depend on s and t. and we had this cross product. And we integrate with respect to the s and t, right? So let's just use what we already found. So we found that we had this vector, so it's z of s and t, y of s and t, and x with respect to s and t. And we multiplied, scalar multiplied right here with respect to the cross product between these two directions, which we found to be just one component, the z component. So if we do that, we are nearly there, but we are missing one bit. We are missing the information about how to move from z to actual s. And for that, we need to remember that the position vector r of s and t was given by s t0, which means that x of s and t was that, and y of s and t was that. That was the coordinates of the position vector, and there was no z coordinate here. So if we substitute it, we will get 0 to 1, 0 to 1, 0. Then we get t, because that was the second component, and then we get s. And we multiply it scalar product way with this. So it already looks simpler. And if we take the scalar product, we get s ds dt. All the rest is gone. And we can use standard techniques from previous maths unit courses to evaluate this double integral. So we do first the s integral, and then time integral, or time parameter t integral, which will give us s squared over 2 from 0 to 1 times t from 0 to 1, which will simplify to give us 1/2. And that is the answer to the integral. So that's how we compute integrals over the surfaces.